Good morning, my YouTube viewers. Crystal here. I've been working on another problem. I've been working on a very small, simple time series problem, and I put it on my GitHub account. So I've got the actual data on the GitHub account, and I've got the program on the GitHub account as well. So you are more than welcome to go in and look at it. I'm just going to try to get this done. Okay. So, the data and the program are both on my GitHub account, so that you're more than welcome to call up my data, and you're more than welcome to call up the program and to look at it and play around with it and experiment if you want to. This is a real live problem, but because it's a real world problem, I can't give you a lot of information on it. So what I will say is your problem statement, training deficiencies for an anonymous department in an organization have been collected from 2016 to 2020. It's worth noting that the COVID-19 pandemic started in early 2020, and this would have an effect on the training deficiencies. So I personally had been collecting this data from 2016 till now, and yesterday I just thought, oh, well, what a great idea. I'm studying machine learning. Maybe I can put this on machine learning and see if I can find something out about it, get some information. So that's exactly what I've done. I've put this information on machine learning. So I can't tell you anything about how I got the information. I can't tell you anything because it's all anonymous, but you're more than welcome to use the information if you want to. So the first thing we had to do was we imported our library. So we imported pandas and NumPy. And then the next thing that we did was we read the file. And this is the file on GitHub. And so the parse states were month, year, and the index column equals month, year as well. And this is all the training deficiency that I collected. I will say that I was sick in the hospital for about 2 months. So when I was sick in the hospital for about 2 months, I just added those 2 months. I just added some figures in there so we wouldn't have any missing data, because I couldn't do anything about that. I was in the hospital against my will. I mean, people who've been watching my videos know why I'm in the hospital, but why I was in the hospital, but I'm not going to discuss it here because this is a technical video. But it was I believe it was in 2019. It was, let me see if I can find it. It was July 19 and August 19. I just had to put some numbers in there because I was in the hospital, so I couldn't be there to collect the data. But other than that, this is real world data. So if you want a real world problem that's really short, that won't crash your computer, that's time series, this is a good problem. And then the next thing we did was we wanted to visualize the data. So I plotted the data on a chart, and you can see how haphazard the data was. It didn't seem to follow any sort of a cohesive problem, except at the time that I'm doing this video, we've been in a pandemic and we've been in lockdown since March 2020. And since we've been in lockdown since March 2020, you'll see that that is creeping up. And that's to do with the lockdown. And again, that's another problem, like whenever you're doing predictions and things like that, sometimes you don't know what's going to happen. Obviously, normal people didn't know that we were going to have a pandemic. And I'm not going to get into the politics of the pandemic here, but obviously when people were making their predictions, they didn't know that we were going to have a pandemic, so they didn't predict on it. But as you can see, in the last 6 months or since 2020, the numbers have been going up, and that's to do with the pandemic. So now what we've done is we've taken this data and we're just representing it another way. So we're showing it on both sides of the axis. Since all of the data was positive, we were able to show it on both sides of the axis. So this is just a different representation of the data. Now what we do is we want to find our x and y values, because we didn't have any missing data, so we didn't have to impute anything, and we didn't have to transform any columns. We didn't have to label and code any columns or transform any columns or anything like that. We didn't have to do any pre-processing, so all we had to do was to define our x and y values. So x is index, factorize 0, reshape, -1, 1. So that's your x value. And your y value is df, training deficiency values. And next thing we want to do, we want to split our training set up for training and testing. So x train, x val, y train, y val equals train test split, x, y. Test size equals 0.3. Random state equals 0. So I could have said 0.33, but I didn't. I just said 0.3. So then we tested our shape. So x train is 37.1, y train is 37, x val is 16.1, y val is 16. Now what we're going to do is we're going to define a model. And I decided to use linear regression on this because through my studies, I found out that you can do linear regression on a time series model. So that's what I decided to do. So we used linear regression, and we got like a 9% accuracy on that. And then when we tested on y val, we actually had a negative accuracy. And so these are the actual and the predicted figures that don't look very well. And so what we did was we plotted a graph. So you can see the graph that we plotted, because this is a time series problem. So I did actually get the code from Jason Brownlee's website to actually plot the graph. So I have to give Jason Brownlee credit. I think his website is called Machine Learning or Master Machine Learning or something like that. But if you do a search on Jason Brownlee, you'll find it. It's got a PhD as well, which I don't have. I only have a master's degree because I wanted to do a PhD, but I couldn't because I left my job, which we won't discuss in this video because it's a technical video. Then what I did was I tried Ridge. Ridge is another type of linear regression, and you can see it was about the same. We had like a 9% accuracy on the x train, y train, and like a negative accuracy on the x val, y val. So these are your predicted values, and you can see that the predicted values are similar to the previous predicted values. And we did another graph, and you can see how the predicted values relate to the actual values. Now, what we did was we did lasso. We decided that we were going to run the model on lasso and see if we could improve our score. But no, we still had like a we had like a 9% accuracy on X train, Y train, and a 46%, a negative 46% accuracy on X val, Y val. You can see these are the actual and predicted values, and they're very similar to the previous one. So we did a chart on that. You can see the chart is very similar. So you can see that these different models that we're using, they're all types of linear regression. So they're very small nuances in the values, but the values are very similar. Next thing we did was we thought we'll use ElastiNet. We'll see, can we get a better figure with ElastiNet? No, we didn't get a better figure with ElastiNet. We got 9% accuracy on X train, Y train, and we got a neg 46% accuracy on X val, Y val. Again, you can see our figures are very similar to the previous figures. Graph, you can see that the graph that we plotted was very similar. Now what I did is, because by this time I was getting a little desperate, so I went on to Jason Brownlee's site, and he had a very simple time series data set on shampoo cells, and then he had the algorithm for that. So I just used the algorithm that he used for this shampoo cells to see if I could get could I get a better accuracy with Jason Brownlee's algorithm. But what I really wanted was sklearn, because that's what I want to use is sklearn. But this is the algorithm that Jason Brownlee in his website Master Machine Learning has used. So you can see that. And then he defined his own X and Y values. And I tried, when I was doing it, I tried to use my X train, Y train, X val, Y val, and it just didn't seem to work out. So these are the X and Y values that he defined. So I decided to go ahead just for this experiment to use the X and Y values that he defined and the function that he defined and the walk-through validation that he defined. And so I got an MSE, mean square error, of 317,789. And so these are the values that we came up with, that he came up with in his particular model. And so what we did, we printed it. We printed this model, and it was the neg 5% accuracy, which I suppose was better than the accuracy that we had gotten from the linear regression. And then you can see the predicted values and the actual values, and you can compare those values and see what you think of them. And then so we did a chart. We put his values on a chart, and you can see how his values related to the actual values. And now what I decided, I always sleep on it. I always work at night, and then I think, okay, well, I'm going to get up in the morning and make a video. And then I slept on it. And then I thought, well, I'm going to try polynomial regression. So this is what we've done. This is what I did. I tried polynomial regression. And it's always good to sleep on things. It's always a good idea, not to put something out right away, to go home and rest, because you might come up with another idea if you go home and rest. So we decided we'd do polynomial regression. We also made a pipeline, and we did polynomial regression to the 4th degree, and we got a 57% accuracy when we did polynomial regression from the 4th degree, and 60% accuracy on the X val, Y val. These are predicted values as compared to the actual values. And this is a plot. We plotted a chart on that. So it looks a lot better when you use polynomial features. It looks a lot better. And polynomial features are quite complex, really. I looked it up on Wikipedia. I know you can't see this, but it says in mathematics, a polynomial is an expression consisting of variables, also called intermediates and coefficients, that involves only the operations of addition, subtraction, multiplication, and non-negative integer exponentiation of variables. An example of a polynomial is a single intermediate. X is x squared minus 4x plus 7. So it's a polynomial. So this, and then if you look on the sklearn website, it gives you some more information about polynomial features. It says the polynomial features, which is what I use, it generates polynomial and interaction features, generate a new feature matrix consisting of all polynomial combinations of the features with degree less than or equal to the specified degree. For example, if an input sample is two-dimensional and of the form AB, the degree 2 polynomial features are 1a, b, a squared, ab, b squared. So that's the information that they actually give you on polynomials in Wikipedia and the sklearn website. So it's more complicated than linear regression. We'll just put it that way. And so here the figure looks a little bit better. It's improved. Our prediction has improved when we use polynomial features. And I just did an experimentation that I want to show you. So I experimented on the 10th degree. So when you experiment on the 10th degree, on the X train, Y train, you get 82.6 degrees of accuracy. But on the X val, Y val, you only got like a 2% accuracy. So although the X train, Y train gave you a really high degree of accuracy because it was training it, you didn't get a high degree of accuracy on the X val, Y val. I think a lot of that to do with the fact that we're in a pandemic, and you know, nobody normal, nobody who's not in the know knew that we were going to have a pandemic. And I do think that the pandemic has actually affected our readings if you weren't in the middle of a pandemic. This is your diagram of the 10th degree. So you decide what you want to do. You just can decide, you know, do you want to use the 4th degree or do you want to use the 10th degree? But I did experiment with the 4th degree and the 10th degree. The 4th degree gives you a better accuracy on the X val, Y val. So I think it's probably best to go with the 4th degree, but you can an extra little taster, And I looked at this Numpy Polyfit, and in order to do the Numpy Polyfit, I had to manipulate my data frame a little bit to give me an index, because the first data frame, my index was the month and the year, but in this particular data frame, I just made an index of 0 to however much was it? 52, so that will give you 53 values. And then what I did was I did this Numpy, and then so I just played around with that a little bit, and I thought that was interesting. And we used the 12th degree, and then so when we put this data into the Numpy Polyfit, into the 12th degree, you can see what happens, and then you can play around with that as well. Go down to 1 degree and then go all the way up, and then you can see how the different degrees work. I think I got up to 15 degrees, and then I don't think it really made a lot of difference after the 12th degree, but you can keep experimenting with the degrees and see how you get on. So that's the solution to this anonymous time series analysis is polynomial features. So, and then I'm just showing you all of the steps that I took to get to it. And in reality, I was just going to not do the polynomial features, but I went to bed and I slept on it. And then I came up with, oh, well, let's test polynomials. And so that's what we're doing. We tested polynomials. And so we got a better polynomial features. So that's it for this presentation. My GitHub account is public, so you're more than welcome to use my data frame because it's anonymous, and you're more than welcome to use my program because it's not that complex. It's very short data frame and very simple program, so you're more than welcome to use it to experiment on it. If you like my video, please like, subscribe, and share. If you like the work I do and you want to leave a donation, I've got my email address for my donation for my PayPal below. I don't have enough subscribers, so I cannot monetize. So that's why I have to ask for donations because I can't monetize. And thank you so much for watching this video, and I look forward to making new videos for you.